So in the previous lecture we talked about types in F#, and in particular we looked at simple types, function types, and then container types. And we looked at tuple and record types, and we saw how we could use generic type variables on those types to create generic containers. In this lecture we're going to expand on these things a little bit and look at something which is generally called algebraic data types, and you will see shortly why that is. So most programming languages have record types, structs, classes, things that you can take small pieces of data and combine them into some larger entity and give that thing a name and a label. And that's one piece of the puzzle. These are generally called product types. So that's why we write the tuple in F# like this star B, because it's the product of A and B. Why this is a product? Well, if you go to mathematics and see how a pair of things is defined, then you will actually end up seeing that mathematically it's a product. It's not A plus. One could easily think naively that A plus B would be the sort of the combination of two elements, but no, it's a product. And for those who are interested in these things, they can go to, for example, and check out category theory, where also these things fall very naturally out, that this is a product. So what is a property of a product? Well, what this really says, if we would spell this out in plain English, it would say A and B. And as I said in the previous lecture, when we have a tuple or we have a record type, which is essentially just a tuple with the named members, when we have this type of structure, this product type of structure, we have to give all the members, each and every one. And that's like really, if you spell it out like this, A and B, that means A and B. It doesn't mean A or B, or perhaps something else. It means exactly this. So if we would draw a slightly sort of a diagram of how this would look, we could say, what is this? If we look at this tuple or this product, we have a set A, we have a set B, and now we have a product set C here down here, which would be, we could say A product B. This is the product set. So we would pick an element from this set A here, and we could draw an arrow and place it into this pair inside of this set. So we pick an element from here and pick an element from here, and we produce a pair. This pair is distinct from picking an element and putting it first and the other one. Yeah, so order matters here. This is the pair of A's and B's, not B's and A's. That's a different product. We can form it, of course, but it's a different product. So there's a difference between the tuple of an int and a float and an int, obviously. Okay. So this is how we form this. Now, if you're a category theoretician, then you know that for every sort of thing with an arrow into it, there's an arrow going back. So you can flip the arrow. So we would say something like this. So now we have two arrows going from this product set. We can have them go to either A or B. Now, if we think about this in terms of functions, it's kind of easy to write this, create the product function. We could just say prod let make product A B equals, well, A star B, or A comma B. This is a function that we could write, right? Very simple. It takes an element from A and it takes an element from B and it produces an element of this thing. Now, if you're here and you want to produce either an A or a B, you have a problem. We can't write that. We can't really write that function in a simple way, because you would call that function and it would have a different return type depending on the case you want. And you can't have both, because then it's not a function. Remember, a function needs to return a single value, one value only. So that's where suddenly this other kind of element comes in, which is something we call a sum type or a co-product. So this is called a co-product, going that way, co-product. And well, most programmers are very familiar, highly familiar with the products and record types. Not so many languages actually have these types, and people are kind of unfamiliar with them. And these are things that are where you can put in either a thing of this kind or that kind. So it's an either-or situation. And then somehow we need to figure out which case it is that it contains. So in order to write this function, this let co-product thing, what we need to do is we need to attach a label to this thing, which has a particular type. So it's one type, but with two cases. And then we can check whether it was case A or case B. And only one of them contains some data. So the other one is sort of void. And we'll see in very shortly how this works out in practice. So this co-product, that gives us something else. It gives us something that we can write A or B instead of star. Or if spell it out in English, A or B. Oh, sorry, B. And this is interesting, because previously we could just say, well, here's the stuff, we need to have this stuff and that stuff and that stuff and that stuff. But now we're able to say in the type system, well, we can have this stuff and that stuff, or this stuff or that stuff. And that gives us a lot of more flexibility, because now we have a whole complete little algebra, a little logic and algebra in our type system. And that's why these guys are together called algebraic data types. And they provide us with a really powerful machinery, because suddenly we can start expressing business logic in our types. And that is kind of important, because it allows us to model our problems in the type system in such a way that the types will guarantee that we have the correct state in our program. We don't need to go in and every time we use this thing go and check, had I defined this and that, or was that empty, or was it null, or any of those horrible things. We know from the definition of the type that the way we get it, it's complete. We don't have to check it anymore, and we can just use it. And functional programmers like to say that there's a mantra that says, make invalid state unrepresentable. And we will look a little bit skim the surface of how this can be done in a little example towards the end of this lecture. So now we have this beautiful type system. So how does one really use these things in practice? We're going to look at that in the next lecture, actually, how we're going to see how to deconstruct these things in code and how they work and so on. But before that, let's have a quick look at some example of how to define these things first, before we try to use them. So, type, as usual when defining a new type, and we can create a type which is called this or that equals. So now we're giving it a name. We can make it we can make it have a generic type parameters as well, or multiple. But in this case, we just make something simple, and then we start naming the cases of this thing, right? So say the first case is this of, say, string, and then we can have another case, that of int, or we can even have something we say neither of nothing. So we don't say anything. That's just the label. Now what this means is that this type, this thing, if I create a value from this, that value can either be a string or an int or nothing at all. This would be where the C programmers, C# programmers would say, okay, it's a null value. But nulls are really, really, really bad for reliability in our code. It's a terrible idea. So instead of this, we have, well, something that doesn't contain any data. And what this means is that when I create the value of this or that, I will say, okay, this is a string, and I said it has this label this. So basically this thing works by saying, in sort of pseudo syntax, it's like creating a tuple. So let x of, this is not real code, but just to drive home the idea, let x of this or that equals, and then I could just say, well, in principle I could represent this as a tuple, so I could say this foo. And now if I would do it like this, I could, every time I get this value, this or that, I could open up this tuple and then I could check whether this is this. And if it is, I could use the value foo as an int. Or if this thing here is a, would be that, then this would be an int and so on. Of course, this you can't do this in reality, but that's basically how you can see it. Is that there are these named cases, and you can go in and check, is it of this kind, of that kind, and or the last kind. And this is something, to do this in actual practice in a language, use something called pattern matching. Which is the topic of the next lecture. And pattern matching is something very simple, so that's nothing to be worried about. We will talk a little bit more about the sort of usage of these algebraic data types instead. So in F#, if I want to create this or that, so let's suppose I want to create some value of this. So I say let A equals, and then I can say this 5. Oh, sorry, this was a string. This foo. I can say let B is a that 5. Let C is neither. This is real F# code. So what you do when you create a type of a discriminant union is that you give the label which case you want and the value that it takes. And these can be complicated values. These can be record types or tuples or whatever, lists. So this is not restricted to some simple type. This can be whatever. But it's just the important thing that we get this label. Or to create that kind, I use that, or to create the empty type, I use neither. So, but the interesting thing is that all of these have the type this or that. This one is a this or that, so that's the type of it. This is just labeling the case of the type. And I know that this is a little bit to wrap your head around before you get used to using these types, because I found them, when I started learning these things, I constantly sort of stumbled upon them because I didn't sort of find it quite natural. So just don't worry. You will just use them, and you will get used to them, and then you can't imagine a life without them anymore. I promise. These are just like having a programming language without union types or discriminant unions is horrible. Once you get used to them, you just get totally addicted to them. So, so before going to the next session and start looking at how to use these types in practice, then how to do pattern matching. Let's look at some examples. The most, I guess, common union type you have, which is in the standard library, standard F# library, is a highly useful type. At first, when you look at it, you go like, what? But I'll try to explain to you why this is so useful. So we can just define it like this. Type option of some generic t equals sum of t, nothing. So this is a type which can take two cases. One has a label sum and contains a value of the type t that you specified. So I could say something like let a equals sum 42, and then that would create, this would have the type int option, or if you like to be more like C# programmers, option int. This is the type of A. I could also create a B, which could be nothing. Oh, sorry, this is Haskell. None. I'm getting languages mixed up. Okay, none. In Haskell, this thing is called maybe, and sum is called just. Same idea. So this particular type here is ultra useful, because suppose now you have a function which might fail. Something simple. We can do the square root. The square root of a negative number is not well defined typically, unless you're working with complex numbers. So what should you return if you do the square root of a negative number? You can't return anything. You could return an error code, but then that doesn't really work well with functions, because how would you do that? You can throw an exception. That's typically what things do. They throw an exception at you. Or you can return an option type. By returning an option type, when you see the definition of your square root function and you see that it returns a float option, you know that this thing can fail. So that already tells you something. The problem with exceptions is that they don't really, you have to go in and either read the code, and really read the code if you really want to know, because if somebody didn't document that this thing will actually accept, then you don't know. Then you don't put a try clause around it, and then it fails, and then it blows up, and your program comes crashing down. The other problem with exceptions is we're lazy, and we're just like, I'm just gonna, it might accept, but it won't, so I just add the checks later, and we don't, and again the thing blows up. The good thing with these option types is that it will return you an option type, and you can't get at the value that you produced without checking whether it was sum or none. You need to do the case analysis. You need to do the happy path and the sad path, and you are forced to, because there's no way of extracting this value without doing it. So you need to check, did I get the value or didn't I? And then you need to take action accordingly. So by returning an option type, you communicate that this thing can actually fail, but we also force you to check for the errors. So this is much better than throwing an exception in general. We still need exceptions though. Because we don't really, when doing I/O, we don't really have no control over things. And then, like, if the file isn't there or the network is down or whatever happens, we need to get an exception back. So those things still have uses, but they are highly abused normally in code. We should be using option types. Right, so that was one example. So let's do a quick little other example. I'm just going to try to do this from the top of my head. Oh yeah, I could say so much about the option type is that there is one, it's a version of it, which is very similar. It's called success, and it has two members, OK of some value and error of some other value, which means that if you have something that fails and you want to communicate back why it failed, you can actually have it return either an error code or a string with the error or some stack trace of something and so on. Very useful. But it's essentially the same thing. So when I said try to make invalid state unrepresentable, let's have a quick look at an example. Yesterday we did a type contact, and we had a first name and we had a last name, string, and then we had we could actually add something like, well, some people have a middle name. Now, what should we put in here if we have a middle name? Well, we could put string, and then we'd say, well, if the person doesn't have a middle name, we'll just have an empty string, and that might be fine. It might not have any consequence, and if we're just printing it, then printing an empty string doesn't really show up. Sometimes, though, we really need to know, and then that ends up having our code full of if contact.middlename equals empty string, then do something else, do something, and that's kind of cumbersome. So what we can do instead is we can now say string option. So now it's optional, and when you read this, you don't even have to be a programmer to read this. You will see that this is optional. And now you need to check whether it contains some value, some middle name, or it's none. So how about the contact? We had a phone. Is it mandatory to have a phone? Well, maybe not. Maybe we make it optional. Email, string, option. But what now? So if this is some contact form, you would probably like to say, well, you need to have either a phone number or an email, or you can have both. Whereas if you would have would you write your type like this, you would know that you have a first name and a last name and a middle name, and perhaps you would have a phone number or an email, but they could potentially be both be none, and then you wouldn't have it, and your type would be actually invalid because it's a requirement in the specification that you be able to contact the person somehow. So how would we solve this? Well, we could create a new type, which we could call contact method, and we can say, well, that can be either phone of string or it can be email of string. So now we can require, by saying instead of having phone and email here, we can say contact method of contact method. And now we need to define a contact method which is either a phone number or an email, and problem is solved. And we can even go further and say, well, both of string tuple string. So then you would know whether you have either a phone number or email, or both have been defined. And now we can see how we are using this and or in order to build a data type which cannot be abused. Once it's defined, we can fully trust in it that it's according to the rules of the specification. We don't have to check whether the contact, every time we use it, whether email was defined or whether phone was defined, and whether they both were not defined, and when, then what, and so on. Because we can be absolutely sure that if we have gotten that far and we have generated a contact, then it will be okay. Yes. So that was that. That was discriminate unions and algebraic data types. And in the next lecture, which I might hopefully record very soon, we will talk about pattern matching, which is actually how we can extract values from these things in our code when we program. And when we're done with pattern matching, then we have gotten pretty far. Pattern matching actually goes much further than just this, so it can be used for a lot of stuff, and it's super useful in a lot of places. So that's why I've decided to put it in its own little session. All right, so until then.